Hi, myself Dr. S.K. Busha. This is a video lecture in physics. The topic is electrostatics and the level class 12. Lesson 5 of chapter 1, electric field. In this lesson, we'll deliberate on electric fields and also work out a few numerical problems. So let's begin. We start with the definition. The space around a charged body within which another charge would be subjected to a force is called the electric field of the charged body. Remarks. We may envisage electric fields set up by a single point charge or a collection of point charges or a continuous distribution of charges. Here, small spheres have been used simply for the purpose of visualization of point charges. In the figure, charge Q establishes an electric field around itself. The bigger circle suggests the electric field of Q. Any other charge Q1, if inside the circle, will experience the field in the form of a force. Regarding the asterisks, subsequently we'll adopt more appropriate representation for electric fields. Thus, the electric field mediates the force between the charges. A charge would produce a field and the field would exert a force on another charge. To summarize, remarks. We could have initiated the discussion with the field of Q1 and then finished with its effect on Q. In order to remove the ambiguity, we refer to the charge of whose field we are interested in as the source charge, Q in our example. The imposter charge is usually a test charge, Q1 in our example. A test charge is a small charge, small enough so that it would not affect the field of the source charge. The necessity of electric fields. Why do we require the concept of an electric field when we could understand Coulomb's law without it? We note that Coulomb's law describes the interaction between 2 point charges in accordance with the action at a distance point of view. That is, interaction between charges is direct and instantaneous. Suppose the source charge starts to accelerate. This will modify its force on the test charge. Experiments have established that the modified force is experienced by the test charge not instantaneously, but after some delay. The action at a distance point of view demands that the modified force is experienced by the test charge instantaneously, thus contradicting the experimental observation. On the other hand, electromagnetic theory predicts that the modifications affected by the accelerating charge propagate in the form of a field disturbance with the speed of light. Therefore, the test charge would know the modifications only after some delay. The concept of the field, therefore, agrees to the experimental observation. Thus, the action at a distance point of view works fine as long as the charges are stationary. Difficulty arises when the charges begin to accelerate. The field point of view, which is an all-weather concept, ultimately replaced the action at a distance point of view for this reason. Operational definition of electric field. The force experienced by a unit positive charge located at a point in an electric field is called the electric field strength, or the electric intensity, or simply the electric field at that point. Let P be a point in an electric field and a test charge Q0 be located there. The force on Q0 is F. Then the electric field at P is limit Q0 tending to 0, force F divided by test charge Q0. Usually, capital E is used to denote an electric field. Regarding the asterisk, the unit positive charge in the SI system is a huge charge and would disrupt the original field by its presence. Hence, the operational definition of electric field is given in terms of a vanishingly small test charge. Clearly, electric field is a vector quantity as it is defined in terms of a force. The SI unit of electric field is Newton per Coulomb. It is also expressed in the equivalent unit of volt per meter. Principle of superposition. Let us consider a collection of point charges Q1, Q2, Q3, etc. P is an arbitrary point in the neighborhood. The resultant electric field at P is the linear sum of fields E1, E2, E3, etc. set up by charges Q1, Q2, Q3, etc. That is, the resultant field E is given by the vector sum E1 plus E2 plus E3 plus ... plus EI plus ... The fields E1, E2, E3, etc. are independent of the presence of other neighboring charges. This is known as the principle of superposition. Electric field lines. Electric field lines are imaginary lines penciled in an electric field subject to the conditions. The tangent to a field line at any point indicates the direction of electric field at that point, and the number of field lines per unit cross-sectional area is proportional to the magnitude of the electric field. Michael Faraday called the field lines as the lines of force and was inclined to describe many of the electrical phenomena in terms of these lines, but will not tread the path shown by Faraday in respect of the field lines. We'll limit ourselves to a qualitative narration and use the field lines only as a scheme for visualizing the patterns of electric fields. Electric field lines of some known charge configurations. Electric field lines for a positively charged metal sphere shown in the figure above. The next figure, electric field lines for a negatively charged metal sphere. Electric field lines for a section of an infinitely large sheet of positive charge. Here, equally spaced parallel lines are indicative of a uniform field. This figure shows electric field lines for a pair of equal and opposite charges. In this representation, unequally spaced lines are indicative of a non-uniform field. Higher density of lines near the charges implies a stronger electric field near the charges compared to the distance locations. And now, some numerical problems. Number 1. Find the electric field due to a point charge. Let us consider a test charge Q0 located at P at a distance R from a point charge Q. The magnitude of the force acting on Q0 may be obtained from Coulomb's law as force F equal to 1 by 4 pi epsilon naught multiplied by Q0 divided by R squared. Therefore, the electric field at P is capital E equal to force by Q0 equal to 1 by 4 pi epsilon naught Q by R squared. The direction of the electric field at P is outward along the radial line from Q if Q is positive. For a negative Q, the direction is inward. Number 2. Find the electric field at a distance Z above the midpoint between two equal point charges, Q is at a distance 2d apart. We have been asked to find the electric field at the location P shown in the figure. Join P with the point charges. The electric fields E1 and E2 due to the point charges are represented by arrows. Clearly, magnitude E1 is equal to magnitude E2. We resolve E1 and E2 into vertical and horizontal components. The horizontal components cancel each other, being equal and opposite, while the vertical components add up, being in the same direction. Therefore, the magnitude of the resultant field is as given. Substituting the value of cos theta, we get this simplifies to the direction of the resultant is in the vertical direction, pointing up as shown in the diagram. Number 3. Two equally charged metal balls, each of mass 10 grams, are suspended from a common point of a rigid support by threads 120 centimeter long. The balls come to rest 5 centimeter apart due to electrostatic repulsion. Find the charge Q on each ball. All charges in a metal ball may be assumed to be concentrated at its center. This is a given condition. The configuration has been illustrated in the following slide. At the equilibrium condition, let the separation between the charged balls be x and the length of each thread be L. Three forces act on the balls. Let's take the ball B for consideration. The three forces are the weight mg of the ball acting vertically down, the tension T acting along the thread towards the suspension point, the electrostatic force between the charged balls Fe acting along the line CB. At equilibrium, the net force on the ball is 0. Therefore, summation of forces in the horizontal direction is also 0. This condition provides Fe equal to T sin theta. Similarly, forces in the vertical direction when summed over is 0, and this gives mg equal to T cos theta. After simplification, we get Fe equal to mg tan theta. We call it equation 3. With reference to the figure, tan theta has been obtained, where we have imposed a condition x by 2 too small with respect to L. Now using equation 3 and 4, we get equation 5. Substituting the numerical values, Q is given as under root the expression. Simplifying, substituting G equal to 10 meter per second square, we get Q equal to 2.40 into 10 to the power minus 8 coulomb. The charges in both the balls may be either positive or negative. Number 4. Two equal charges Q are kept fixed at coordinates minus a, 0 and at coordinates plus a, 0 along the x-axis. A particle of mass m and charge Q by 2 is brought to the origin and given a small displacement along the x-axis. Describe the subsequent motion of the particle. Let the particle be displaced through a small distance x along the x-axis. The particle experiences two forces. One due to the charge at coordinates minus a, 0, which points in the direction of x-axis, and the other due to the charge at coordinates plus a, 0, which points in the direction of negative x-axis. The force due to the distant charge is smaller than that due to the nearer one, and hence the resultant force F points to the origin. Its magnitude is given by force due to the nearer charge minus force due to the distant charge. Expressing it in terms of symbols, we get a further simplification will yield as x is too small with respect to a, the force F can be expressed as 1 by 4 pi epsilon naught 2q square divided by a cube multiplied by x. We have observed that the force F on the particle is proportional to its displacement x. The origin O is the position of equilibrium as F is equal to 0 when x is equal to 0. The force F points to the origin. Therefore, the particle will execute a simple harmonic motion, in short SHM, about O along the x-axis. Number 5. Here we will pronounce small q as q and capital Q as capital Q. Then the problem 5 will read as 3 charges 4q, capital Q and Q are in a straight line in the positions 0, L by 2 and L respectively along the x-axis. For what value of capital Q will the resultant force on Q be 0? The force on Q exerted by the charge for Q points along the positive x-axis. Therefore, to make the resultant force on Q 0, the force exerted on it by capital Q must point along the negative x-axis. This implies that capital Q is negative. Equating the magnitudes of the forces, solving, we get capital Q equal to Q in magnitude. Putting the appropriate sign, we get capital Q equal to minus Q. Number 6. 4 charges are arranged at the corners of a square ABCD as shown in the diagram. Find the force on a charge plus Q kept at the center of the square. Let us denote the forces exerted on the charge plus Q at O by the charges at A, B, C, and D respectively as FA, FB, FC, and FD. The center O is equidistant from the 4 corners of the square. We can see that the pair of forces FA and FC are mutually equal and opposite, and they cancel out. So is the pair FB and FD. Therefore, the net force on the charge plus Q at O is 0. With this, we have come to the end of the lesson 5. We'll cover continuous charge distributions, electric flux, and Gauss's law in the next lesson. Till then, goodbye and thank you.